Fine. So আমরা আসলে last class-এ infinite long rod-এর জন্য use করে আসলে basically how we have to find out that electric field for different shape of object using the Gauss's law. That thing we discuss. So today I'm going to talk about this is very important thing actually that we have to use in the case of electric potential. So can you see my screen properly?
Yes, sir.
Okay, fine. So we're going to talk about today an infinite plane sheet of charge. Infinite plane sheet of charge. What is that? So we have a plane sheet like that. So into that sheet, say this is uniformly distributed, right? Then due to that charge, we're going to, and we define that this is that surface charge density, surface charge density, which is expressed by sigma. That would be charge per unit area. Say the total charge in that sheet is Q and the area of this sheet is A. Then this is would be actually that surface charge density, which is defined coulomb per meter square. This is one parameter we have to use for this two-dimensional case, surface charge density. Now to find out that electric field for this plane sheet, what I'm going to do, I'm going to take, say, this is that sheet one side, and we can say this is the charge at that side, right? So this will be charge. Now to find out that, say, sheet is basically that one, I change, this is one side of the sheet, another side, say, into the screen. So if it is the case, then I am going to find out that electric field for this infinite plane sheet. So I know the charge of this sheet is Q. To find out that one, I'm going to choose the Gauss's law. So for that one, I'll choose a closed Gaussian surface. So one side is that direction. This is actually my Gaussian surface for that direction, and another surface is toward that direction. So that's mean this Gaussian surface in the both two side of this sheet, left side and right side of that sheet. So I'm going to label this surface. This is surface 1, and this is surface 2, and say this is surface 3. That's why I label that one. Since it's a positive charge, then I can say that this is basically the electric field direction, right? This is the direction of the electric field. This will be from away from, and also for that direction is going to be towards that direction. Sorry, it should be straight. This is the direction of my electric field. Now I have to find out that area vector for these three surface. So since this is one surface which is S2, I'll find out area vector will be towards that direction, right? Radially outward from, sorry, say DA2. And for S1 would be towards that direction, inside to outside. This is actually the direction of the area vector, since area is a vector. And for this curved surface, which is S3, it will be always towards that direction, not say at that point it be toward that direction. If you think about that point, that should be out of the screen. If you think about that point, it would be downward. If you think about on the back side of this curved surface, which would be into the screen. So this is actually that. That's when this surface area is always perpendicular to that surface. It will be always. Whenever the point you want to find out the area of that point, the direction of this area will be always perpendicular to that surface. Fine. Now I'm going to use my Gauss's law to find out that one. So my Gauss's law is said that one E dot dA must be equal to Q enclosed divided by naught, right? This is enclosed charge. What we are going to do in that case, we'll write this is would be surface 1. I'll write then this is my electric field. Electric field is constant, it's not changing. So this is the electric field. So I'll write down this is actually that D1. I'll just separate by this according to that surface. This is for S2. I'll write E into dA2 plus S3. It would be E dot dA3 must be equal to total charge, which is Q into that infinite plane, is going to be that epsilon naught. Now look at this. This dA1 and this electric field vector are parallel to each other, right? For surface S1 and for surface S2. But for surface S3, it is perpendicular to that electric field vector. So that's mean the angle between these two vectors is 90 degree over here. An angle between these two over here for that surface 2 is 0, and surface 1, it is also the 0. That's why I can say that for surface 3, this part would be basically the 0, because angle between these two vectors is 90 degree and cos 90 basically that 0. Then I can write this one would be E into enclosed dA, right? Why? Because this is I'm writing in that form. Dot product of these two vector A dot B is basically AB cos theta. Since they are parallel, the theta is 0, so cos 0 basically the 1. And since the electric field is constant, I factor out of this integration because area is changing. So that's why I write down this one plus E into integration of dA 2 must be equal to Q by epsilon naught. Right? Can I write this one? Now, if we integrate, I will find out this should be basically that E into E1 plus E into E2 must be equal to Q by epsilon naught. But since we choose that same Gaussian surface on the both two sides, then the area of A1, area of A2, and area of A3 must be the equal, right? So then we can write EA plus EA equal to Q by epsilon naught, since A1 equal to A2 equal to the A we consider. Then we will find out 2 into EA. Then Q we can write because we define that surface charge density actually charge per unit area. So that's when Q would be sigma into A divided by epsilon naught. Right? Now this A will be cancelled out. Then we'll find out twice E basically is sigma by epsilon naught, and for E would be basically sigma divided by twice epsilon naught. So that is to be strength of this electric field for infinite long sheet, which has a positive charge. And this is a very important formula. We have to use this one. So that's mean if you have a long infinite plane, in that case, that electric field for this plate would be sigma by twice epsilon naught. where sigma is basically the surface charge density. Sometimes we can write down, say, in terms of vector. So we have to express that one. Say if I choose that form, say plus plus plus, this is 1 direction. If you consider, say, this is actually that positive x direction, and say this is actually positive y direction. In that case, this vector will be towards the positive x direction. I should write, say, I hat, and this one would be basically minus e into I hat, right? We can write down in that form. Then we can generalize this equation in a form. So E is basically sigma by twice epsilon naught r hat when x is greater than 0, right? Or E is basically minus sigma by twice epsilon naught I hat when x is less than 0. That's why actually you can find out this electric field for infinite long sheet for uniform charge distribution. If it's non-uniform, then the process are same, but the equation format will be the different. Okay, fine. Let's apply application of this one. Say we have a, think about this, a parallel plate capacitor actually. In the parallel plate capacitor, we have a positive plate, right? And another case, we have a, I can use the negative plate for different color. Then it should be easier for me. So this is that negative plate. In that place, there are equal amount of charge, but in the opposite polarity, right? I have to find out what will be that electric field. So in the parallel plate capacitor, we use that plate, consider an infinite long plate, because these two plates are very close to each other inside a capacitor, right? Did you ever see the capacitor? Capacitor physical dimension is like that. You have a cylindrical outside, and into that cylinder you will find out there will be some plate. One is positive plate, another is basically the negative place. This dimension is, the distance between this one is very small, very small. I draw that on a bigger so that you can understand. Then there is a positive plate and another is the negative plate actually, right? So I am to find out what is the electric field for this parallel plate capacitor. So I know, since if you consider that parallel plate capacitor, then the electric field, the magnitude would be basically sigma by twice epsilon naught, right? This is actually magnitude. Then I can draw that one. So this is to be for positive 1. And it is also constant, it's not changing. Look at this, it is independent of that position, right? So that's mean magnitude would be same in everywhere. So this is that one, and this is would be also that one. Now for, if you consider for the negative charge, the electric field strength are same, but it would be basically in the opposite direction, right? So strength will be sigma by twice epsilon naught, that we write down over here, that we write. Then for the negative source charge, I know that electric field will be towards the direction of the plate, right? This will be towards, this will be also the towards, and this will be also that towards, right? Now we can consider these two vector, plus and minus, actually basically they equal, but in the opposite direction, these two vectors. So that's why they will cancel out, and this will also cancel out outside that capacitor actually. So that's mean outside the capacitor there will be no electric field. There are also some, is called the fringe effect over here. We neglect that fringe. If the these sheets are infinitely long, then the age effect or the fringe effect actually is called, because this one will be try to come into that direction at the side of this one. This is called the age effect or the fringe effect actually. We will neglect that one if that your capacitor plate is infinitely long, then we can neglect this fringe effect for that parallel plate capacitor. We'll consider that one. Sorry. We'll consider that one infinitely long sheet. Fine. Then what would be that electric field inside? Electric field inside would be basically one is for positive. So that is actually that E divided by twice epsilon naught plus another is sigma by twice epsilon naught, right? Then it should be basically 2 into sigma by twice epsilon naught. These two will be cancelled out. We can find out it would be sigma by epsilon naught. So that should be basically that electric field strength inside a parallel plate capacitor. For single plate, infinite long sheet is basically sigma by twice epsilon naught. And for parallel plate capacitor, which is the positive and the negative, that electric field inside that parallel plate capacitor would be sigma by epsilon naught. This formula is very important. We have to use this formula in the case of potential. We'll use that in the next class, actually, or the potential chapter 24. We have to use this equation. So that's why I shown you how to derive that formula, where it's come from actually. If you forget about it, you can derive in that way actually, this formula. You understand? Yeah, now think about what will happen, say, if my parallel plate capacitor, both one is positive. If both one is positive or both one is negative, then what will happen actually? Then you can find out, look at this, if you draw the electric field for this positive one with that direction, this would be towards that direction. I should use the difference. Exactly, exactly, right? So if it's that positive one, then for that one it should be positive away from that. This one would be positive away from that. This one would be also that positive away from that. And I have to also draw one more line for this black one. This is would be also away from that. Then these two are basically opposite direction, so they will cancel out. Right, so they will cancel out over here. You'll find out only outside that electric field would be magnitude will be the same, right? So that's when you will find out the electric field only outside of this parallel capacitor if the both plate are positive or the negative. That's why we use one leg is positive and one leg actually the positive in the case of parallel plate capacitor. So do you have any question over here? No question.
পেইজেরটা স্যার গাউসিয়ান সারফেসটা আপনি সিলিন্ড্রিক্যাল আঁকলেন কেন?
কোনটার জন্য?
পেইজের জন্য যেটা দিলেন শীটের জন্য।
হ্যাঁ হ্যাঁ হ্যাঁ।
সিলিন্ড্রিক্যাল শেপ আঁকছেন কেন?
Yes, exactly. This one cylindrical. Otherwise it won't be the close.
তো পেইজেরটা শেপে হবে না, মনে করেন যে শেপে আছে ওই শেপে হবে?
No. It has to be the close. It has to be the close. It will be easier for me. Yeah, you can do that by that shape of the base. Then you have to integrate for more than that. The integration would be basically the difficult for if it is the shape of the base actually. Right, because what would be in that case, say if you think about the base, you will find out for the two surface, say the left or right. What about that top, bottom, and front and back? How do you enclose that one? Right, did you get my point, what I'm going to say?
Yes.
So that's why it would be better to choose the cylindrical crossing surface. And in a cylindrical Gaussian surface is very straightforward. You can find out in that way. So this is actually end of this basically the theory part of this Gauss's law. Now say I'm going to talk about a problem I choose. Basically, which one I will start for first for you. I don't know which one will be easier. Well, let's do this one. This is very simple but interesting. I'll look at this. Although I basically solved this problem in the case of your solve problem in the BUX, you can go through that one, you will find out that one. So I'm going to consider for this case, say this is say that the electric field in a particular space E equal to x plus 2I Newton per Coulomb, where x in meter. Basically, electric field will be the change. X is the position over here. Consider a cylindrical Gaussian surface of radius 20 centimeter that is coaxial with the x-axis. One end of the cylinder at x equal to 0. What is the magnitude of the electric flux through the other end of the cylinder at x equal to 2 meter? And what is the net charge enclosed within that cylinder? You understand what they are saying? Saying that basically, say I choose say is the case. So one surface, this is the electric field. If I draw that line of the electric field, this is the direction of the electric field for this cylinder, which is E. Now it say that this is the surface. One surface is say this is x equal to 0 at that point, and this is x equal to basically 20 centimeters. Sorry, I am convert to the meter. 2 meter. This is 20 centimeter given over here. Now they asked me find out that one end actually that flux, what will the flux for other end at x equal to 0.20 meter over here. Fine, I will assume that this is the surface. Say I will label that surface by the same analogy we will follow, the same procedure I follow. So this is surface 1, this is would be surface 2, and this is would be surface 3. If you draw for that surface, that this is would be your area vector, right? For this is would be your area vector dA1, and for this one, this is would be your area vector perpendicular to that region. So this is actually that A2. But the electric field, we draw that electric field is toward that direction, right? So inside that cylinder. Now I'll find out that flux by the same analogy I talk about. Say that total flux E dot dA must be I'm going to find out the flux from there, not the charge. So that's why only the formula I'm going to use is not, because I don't know the how much charge inside over there. So I'll use that one. So then this could be write down the total flux. Basically would be, I should write, this is the electric flux equal enclose E dot EA. This is for surface 1. E dot DA1 plus, and this surface I have to find out actually, say when the surface would be 1, when x equal to basically the 0, right? If the x is different, then the surface is going to be the different, right? Plus for surface 2, say this is surface 1, for surface 2, which would be E dot dA2, provided x limit would be from, I should write down the range, in between that value. So x is greater than, I did it in another way actually in your video, or you can write. And for S3, which is E dot dA3, when x equal to 0.2, right? Because if you change that value of the x, your surface would be different, because your electric field also that depend on this position of the x, which is x plus 2y. I choose, say this is my
x এর পার্টটা
x.
আরেকটু বুঝাবেন।
Which one?
x এর পার্টটা স্যার এক্সটা কেমনে চেঞ্জ হচ্ছে?
আচ্ছা দেখো এখানে বলছে এইটার লেন্থ হইছে, এখানে বলে দিছে দেখো, এই যে ওয়ান এন্ড অফ দ্য সিলিন্ডার ইজ x ইকুয়াল টু 0। এই সিলিন্ডারের একটা এন্ড হচ্ছে x ইকুয়াল টু 0 তে, আরেকটা এন্ড হচ্ছে তাহলে x ইকুয়াল টু 0.2 তে হবে, যেহেতু লেন্থটা হচ্ছে 20 সেন্টিমিটার। Sorry, 20 centimeter হচ্ছে radius. I'm sorry, extremely sorry. This is the radius of this Gaussian surface is 20 centimeter. This is the R, and this is the 2 meter. It's not 0.2. I'm sorry. This will be the 2 meter. X equal to 2 meter. It's 2. This is also 2. এখন দেখো তোমার এই সিলিন্ডারটা স্টার্ট করছে আসলে x equal to 0 থেকে 2 মিটার পর্যন্ত, রাইট? এখন এই সারফেসটা বেসিক্যালি যখন x এর ভ্যালু 0 তখন তুমি s1 পাবা, যখন x এর ভ্যালু 2 তখন তুমি এই সারফেসটা পাবা যেটা হচ্ছে s3, আর x এর ভ্যালু যখন 0 থেকে শুরু করে 2 পর্যন্ত থাকবে, স্টার্টিং ফ্রম দ্যাট পয়েন্ট টু দ্যাট পয়েন্ট, তখন তুমি s2 টা পাবা, রাইট? এটা বুঝা গেছে? আচ্ছা, যেহেতু আমার দেখো ইলেকট্রিক ফিল্ডটা ভেরিয়েবল, এক্স এর সাথে ডিপেন্ড করবে, এই জন্য আমাকে এই কন্ডিশনটা আসলে এখানে দিতে হবে। এখন এই ফর সারফেস 2 বেসিক্যালি ইলেকট্রিক ফিল্ড এবং হচ্ছে তোমার এরিয়া ভেক্টর আর পারপেন্ডিকুলার টু ইচ আদার, রাইট? এটা হচ্ছে তোমার ইলেকট্রিক ফিল্ডের ডিরেকশন, আর এইটা হচ্ছে এরিয়া ভেক্টর। তাহলে এই অ্যাঙ্গেলটা কত? 90, এন্ড cos 90 বেসিক্যালি উড বি দ্য 0। সো দ্যাটস ওয়াই S2 এর জন্য আমি আসলে ইলেকট্রিক ফিল্ড বা দ্য ফ্লাক্সের কন্ট্রিবিউশন আসলে 0 পাবো।
ওকে স্যার।
ঠিক আছে?
জি স্যার। যে কোনো সিলিন্ডার যদি দেখি আমরা, এটা না লিখলেও তো সমস্যা নেই, এটা তো প্রুফ করতেছেন, জাস্ট সূত্রটা বসায় দিয়ে উত্তর লিখে দিলেই তো হলো।
নো সামটাইম করতে হবে, ভেরিয়েবল হলে এটা করতে হবে।
আচ্ছা,
সিনারিও কুড বি ডিফারেন্ট। ভেরিয়েবল ফিল্ড হলে এটা দেখতে হবে, এই জন্যই আমি প্রসেসটা দেখাচ্ছি। এটা তো খুব একই প্রসিডিউর আমরা ফলো করতেছি, এটা করা বেটার।
ওকে স্যার।
আচ্ছা এখন দেখো এখানে ই এবং ডি এ বেসিক্যালি সারফেস 1 এর জন্য আমার ইলেকট্রিক ফিল্ড হচ্ছে এই দিকে আর এরিয়া ভেক্টর হচ্ছে এই দিকে, তাহলে তাদের মাঝখানে অ্যাঙ্গেল কত?
স্যার কোনটার জন্য স্যার?
সারফেস 1 এর জন্য
সারফেস
এটা হচ্ছে এরিয়া ভেক্টর হচ্ছে এই দিকে, এই যে দেখছো 0 বলে ফেলতেছে না বুঝেই।
সরি স্যার, এটা হচ্ছে 180।
180 ডিগ্রি, এই জন্য এটা করতে হবে। তাহলে cos of 180 ডিগ্রি মান কত?
মাইনাস
-1, রাইট? তাহলে আমি আর ফর্মুলাটা লিখলাম না, তাহলে এটা আমি ওই a ডট b ইকুয়াল টু ab কোসাইন থিটা ওখান থেকে লিখছি। ঠিক আছে, এখানে ডট ছিল প্লাস, আচ্ছা প্রোভাইডেড এখানে আমার লিখতে হবে x ইকুয়াল টু বেসিক্যালি 0, সরি প্লাস এটা তো 0ই, প্লাস এখানে যেটা আমরা পাবো এখানে হচ্ছে অ্যাঙ্গেল কত সারফেস 3 এর জন্য?
সারফেস 3 এর জন্য হচ্ছে স্যার 0 ডিগ্রি।
0 ডিগ্রি। So I'll find out E3 at x equal to basically 2. ঠিক আছে, এখন তুমি আসলে বের করতে পারবা। আমি আসলে এটা টোটাল ফ্লাক্স বের করতেছি। এটা হচ্ছে এই সিলিন্ডারের টোটাল ফ্লাক্স। তুমি আলাদাভাবে ওরা বের করতে বলছে আসলে এইখানে যখন x equal to 2 আদার সাইড অফ দ্যাট, এই যে বলছে হোয়াট ইজ দ্য ম্যাগনিটিউড অফ দ্য ইলেকট্রিক ফ্লাক্স থ্রু দ্য আদার এন্ড অফ দ্য সিলিন্ডার। তাহলে আমি
একটা
হ্যাঁ এই কোশ্চেন আমাকে একটা বের করতে বলছে x equal to 2 তো ফ্লাক্স কত হবে। এটা তাহলে আমার কনসিডার না করলে চলবে, তারপর আমি দেখাচ্ছি আর কি যাতে তুমি করতে পারো। তাহলে E ইনটু হচ্ছে A1 when x equal to 0 plus E into A3 when x equal to 2. আমি এখন এটার ভ্যালু বসাবো, এটা কাজে লাগবে আমার সেকেন্ড পার্টে আসলে। তাহলে এখানে দেখো ইলেকট্রিক ফিল্ডটা কত, x প্লাস ছিল আমার 2 রাইট ইনটু A1 at x equal to 0, আমি প্রত্যেকটা স্টেপ বাই করতেছি, x plus 2 into A3 at x equal to 2 basically. নাও আমরা x এর ভ্যালু বসাই দিব, x এর ভ্যালু বসাই দিলে এখানে আমি পাবো হচ্ছে -2 into A1 আর এখানে পাবো হচ্ছে 4 into A3। বাট আমরা তো জানি এই সিলিন্ডারটার A1 A3 আর ইকুয়াল হবে না, সেম হবে না
জি স্যার।
রেডিয়াস। তাহলে তখন আমরা এটা বলতে পারবো আসলে
কোনো চেঞ্জ আসবে না
কিসের জন্য,
x এর ভ্যালু যে আলাদা হইতেছে।
হ্যাঁ চেঞ্জ তো হলোই।
আচ্ছা, এর জন্য 2 আর এর জন্য
হ্যাঁ এখানে দেখো 0 plus 2 হলো 2 আর এটার জন্য 2 plus 2 হলো 4।
আচ্ছা স্যার।
তখন আমি পেলাম এটা হবে আসলে টুয়াইস এ টোটাল ইলেকট্রিক ফ্লাক্স। কিন্তু যদি আমি রাইট সাইডে বের করি তখন রাইট সাইডের জন্য এইটা এতটুকু লাগবে শুধু আমার, যখন x equal to 2 তে রাইট। তাহলে সেটা আমি বলি, তাহলে ফ্লাক্স E at x equal to 2 I'll find out 4a। তাহলে 4a হবে কি পাই ইনটু r স্কয়ার রাইট, পাই ইনটু 3.14 ইনটু r হচ্ছে তোমার 20 সেন্টিমিটার হুইচ ইজ 0.2 স্কয়ার। তাহলে তুমি যদি এটা করো তাহলে তখন তুমি পাবা আসলে 0.5 Newton meter square per coulomb. So this is the answer of that first one. The second one says what is the net charge enclosed by that cylinder? A net charge, to find out we'll write down this one. Net electric flux would be Q enclosed divided by epsilon naught, right? Gauss's law থেকে আমরা এটা লিখলাম।
একটু ইন্টারাপ্ট করি স্যার। মানে ওই যে ইয়েতে চিত্রতে হচ্ছে আপনি যে মানে ডিরেকশনটা দিছেন ইলেকট্রন ফ্লাক্সের, এই ফ্লাক্সের ডিরেকশনটা কেমনে দিলেন, এর ডিরেকশনটা?
এটা বলেই দিছে আমাকে, দেখো এই যে E equal to x plus 2 into I head। আমি এটা ধরে নিয়েছি এইটা হচ্ছে এইদিকে হচ্ছে আমার পজিটিভ x এক্সিস রাইট ওয়ার্ড, ঠিক আছে?
আচ্ছা ওকে স্যার।
এটা হচ্ছে আমার পজিটিভ x এক্সিস, তাহলে ইলেকট্রিক ফিল্ডটা টুয়ার্ডস দ্য কোন দিকে, দেখো এই যে বলে দিছে x এর দিকে।
আচ্ছা স্যার।
হ্যাঁ এই জন্যই আমি ওইদিকে ড্র করছি, ঠিক আছে?
জি স্যার।
Then I can find out this enclosed charge would be epsilon naught into finite, and finite হচ্ছে আমার এটা, এই জন্য আমি finite বের করেছি। finite হচ্ছে আমার এই যে এটা প্লাস 2a, ঠিক আছে?
জি স্যার।
তাহলে এখান থেকে তুমি বের করতে পারবা, সেটা হচ্ছে epsilon naught এর ভ্যালু হচ্ছে আমি একবার বসাচ্ছি, সেটা হচ্ছে 8.85 into 10 to the minus 12 আর ফাইনাল হচ্ছে 2a, 2 into a হচ্ছে 4 pi r square, right? Sorry, this is the 2a pi r square, area হবে pi r square, not the 4 pi r square, it's a pi r square, pi is 3.14 into r হচ্ছে 0.2 centimeter. Then you will find out the Q enclosed would be in your case 2.22 into 10 to the minus 12 coulomb. This will be the answer of this question. Okay, now you can see that problem actually that are in the BUX. We solved 7 problem over there for this Gauss's law. Go through that one, then you will understand. If you face any problem, just give me a knock in the Slack.
Okay, sir.
Okay, do you have any more question?
No, sir.
Then you can leave. Done for today.
Assalamualaikum, sir.
Wassalam.